Imagine the universe, everything we know and don't know, compressed into a space smaller than a grain of sand. This is the mind-boggling beginning proposed by the Big Bang Theory, the prevailing model for the origin of our universe. It's a story that spans billions of years, from an unimaginably hot and dense state to the vast, ever-expanding cosmos we observe today. The Big Bang Theory is not just a whimsical idea, but a robust scientific model supported by a wealth of observational evidence. Understanding the Big Bang is not just about grasping the universe's history, but also about comprehending our place within this grand cosmic narrative. By piecing together the remnants of this ancient explosion, scientists have been able to construct a timeline of the universe's evolution, revealing the key events that shaped the cosmos and ultimately led to our existence. It's a journey that takes us to the very edge of human understanding, forcing us to confront the profound questions about our origins and our place in the grand scheme of things. At the heart of the Big Bang Theory lies a concept that is both fascinating and incredibly challenging to grasp: the singularity. Picture, if you can, all the matter and energy in the universe compressed into an infinitesimally small point, an entity of unimaginable density and temperature. This is the singularity, the seed from which our entire universe sprang forth. Think of a balloon deflating. As it shrinks, the dots you drew on its surface get closer and closer together. The singularity represents a breakdown of our current understanding of physics. The laws that govern the universe today, such as gravity and quantum mechanics, cease to function at such extreme conditions. Despite these challenges, the singularity remains a cornerstone of the Big Bang Theory, a crucial starting point for understanding the universe's evolution. It represents a point in time beyond which we cannot currently see, a realm where the very fabric of space-time is thought to have been intertwined. The Big Bang wasn't an explosion in the traditional sense, like a firework going off in the vast emptiness of space. Instead, it was the rapid expansion of space itself, an event that marked the beginning of time and the universe as we know it. Imagine a tiny dot suddenly inflating, with every point moving away from every other point at an incredible speed. In the first fleeting fractions of a second after the Big Bang, the universe was an unimaginably hot and dense soup of energy. Temperatures soared to trillions upon trillions of degrees, far hotter than anything we can create in our most powerful particle accelerators. As the universe expanded, it cooled, and energy began to transform into matter. From this primordial soup of energy and matter, the foundations of our universe began to emerge. The first elementary particles, the building blocks of all matter, flickered into existence, setting the stage for the formation of atoms, stars, galaxies, and everything we see around us today. In the first fleeting fraction of a second after the Big Bang, something remarkable happened. The universe underwent a period of exponential expansion known as inflation. Imagine a balloon suddenly inflating to an astronomical size in a fraction of a second. That's the essence of cosmic inflation. This rapid expansion, driven by a still mysterious force, smoothed out the early universe, stretching out any initial wrinkles or irregularities. This process helps explain why the universe we observe today is so remarkably uniform on the largest scales. Inflation had a profound impact on the evolution of the universe. It stretched quantum fluctuations in the early universe into vast cosmic structures, providing the seeds for the formation of galaxies and galaxy clusters. It's like taking tiny imperfections on the surface of a balloon and stretching them into mountains and valleys. While the exact mechanism driving inflation remains a topic of active research, the concept has become an integral part of the Big Bang Theory, explaining several observed features of the universe that were previously puzzling. As the universe continued to expand and cool, the energetic soup of particles began to settle down. The intense heat of the early universe gradually subsided, allowing for the formation of more stable particles. This era marked a crucial transition from a universe dominated by radiation to one increasingly influenced by matter. Protons and neutrons, the building blocks of atomic nuclei, began to clump together in a process called nucleosynthesis. Imagine a dance floor where dancers, or particles, are moving too fast to pair up. As the music slows, or the temperature cools, they can finally come together to form stable pairs, like protons and neutrons. Despite these obstacles, a significant amount of helium, along with trace amounts of other light elements like lithium and beryllium, were forged during this period. The formation of these first atomic nuclei marked a crucial step in the universe's evolution. It laid the groundwork for the formation of atoms, the basic building blocks of matter as we know it, and set the stage for the emergence of stars, galaxies, and eventually life itself. As millions of years passed, gravity, the architect of the cosmos, began to exert its influence on the expanding universe. The tiny density fluctuations, amplified by inflation, acted as gravitational seeds, pulling in surrounding matter and gradually forming vast cosmic structures. Imagine a sprinkled surface like flour on a countertop. Now, imagine those sprinkles clumping together under an invisible force, creating a web-like pattern. This is similar to how gravity sculpted the universe. Within these dense clumps of gas and dust, stars ignited, flooding the universe with light and warmth for the first time. These early stars, much larger and hotter than our sun, played a crucial role in shaping the evolution of galaxies and seeding the universe with heavier elements. As stars clustered together, drawn by their mutual gravitational attraction, the first galaxies began to take shape. These swirling collections of billions of stars became the building blocks of even larger structures, forming clusters, superclusters, and vast cosmic filaments that stretched across the universe like a giant web. Stars are the cosmic engines that drive the evolution of galaxies and the universe as a whole. Within their fiery cores, stars forge heavier elements from lighter ones through the process of nuclear fusion, releasing vast amounts of energy in the process. Think of stars as giant cosmic kitchens, cooking up the ingredients for planets, life, and everything we see around us. Stars are born from the gravitational collapse of massive clouds of gas and dust. As these clouds contract, they heat up, eventually reaching temperatures and pressures high enough to ignite nuclear fusion in their cores. The life cycle of a star depends on its mass. Massive stars live fast and die young, exhausting their nuclear fuel quickly and ending their lives in spectacular supernova explosions. These explosions seed the surrounding interstellar medium with heavier elements, enriching the material from which future generations of stars and planets will form. Smaller stars, like our Sun, live for billions of years, steadily fusing hydrogen into helium. Eventually, they too will exhaust their fuel, expanding into red giants before shedding their outer layers, leaving behind their dense cores as white dwarfs. Our place in the cosmos began about 4.6 billion years ago, in a relatively quiet corner of the Milky Way galaxy, when our own solar system started to form. It all began with a giant, rotating cloud of gas and dust, a nebula enriched with the remnants of countless previous generations of stars. Imagine a spinning disk of pizza dough. As it spins, it flattens out, much like the solar nebula did billions of years ago. This spinning disk would eventually give rise to our Sun and the planets. At the heart of this swirling cloud, gravity drew in more and more material, causing the central region to collapse under its own weight. As this protostar contracted, it spun faster and faster, eventually becoming hot and dense enough to ignite nuclear fusion, giving birth to our Sun. Meanwhile, in the outer regions of the protoplanetary disk, dust grains collided and stuck together, gradually forming larger and larger clumps. These clumps, through a process called accretion, grew into planetesimals, the building blocks of planets. The Big Bang theory is backed by a wealth of observational evidence. This evidence comes from various sources, each offering a unique window into the early universe. One compelling piece is the cosmic microwave background radiation, the afterglow of the Big Bang. Discovered in 1964, it's a faint whisper of radiation from the universe's hot beginnings. Another crucial piece is the observed abundances of light elements like hydrogen, helium, and lithium. Further support comes from the observation that the universe is expanding. The Big Bang theory offers a compelling explanation for the universe's origin, but it's a work in progress. Many unanswered questions continue to intrigue cosmologists. Dark matter and dark energy remain two of the biggest mysteries. We infer their existence through gravitational effects, but their true nature is unknown. Another puzzle is the nature of the singularity itself. Understanding it may require new physics, unifying gravity and quantum mechanics. The Big Bang theory revolutionized our understanding of the universe, transforming our view of our place in the cosmos. It tells us we live in an evolving universe, from a hot, dense fireball to the vast cosmos we observe today. The atoms in our bodies were forged in stars or during the Big Bang itself. The Big Bang